vector, its position is irrelevant. It's just its length and its direction, its magnitude and direction. So I can select this one and right click, vector, copy. Now we agreed that there is a rule for adding vectors, which is that you add the x's and you add the y's. Therefore, adding these two vectors is simply going to be this diagonal up here. So that one, and that one, and this point, and right click, vector. Now we've got to subtract those as well, we haven't got there yet. Add vectors. Aha. What happens if I move this around? It's still the diagonal of the parallelogram, and it is a parallelogram, of course. Now what about subtracting? Well, is it possible that we can pick this up? Just sort of think about this for a second. If you've got the number 3 and you add it to -3, what's the answer? The answer is 0. So in ordinary arithmetic, we have a rule for adding numbers, but if we have a rule for a negative number, to which if we add it to its positive equivalent, you get 0. So we want to do the same thing with vectors. So let's pick this one up and see, is it possible that we could move it around until the addition is 0? Aha, there it is. So the subtraction is simply going to be the same as this one, but going in the opposite direction. So you did minus it and minus it here. So if we take this vector here and this point here and right click vector to a negative vector, now if we add this one to this one and put it here, if we add them, we are effectively subtracting them. So we could easily, just as easily, taken these two and put the answer here. Vector add. Oh boy, now that's pretty remarkable, isn't it, that the sum of two vectors is this diagonal and the difference is this diagonal. I just think that's quite a nice way of introducing vectors, and from then onwards they're quite harmless really. They're very powerful and very, very useful, and they exist in 3 dimensions as well. This is a 3D of autograph, and let's just put a plane on to start with. Let's do our over in 2x minus 3y equals 6. It's a straight line in 2 dimensions, but in 3 dimensions it's a plane. Now if we turn it around like that, that's what it looked like in 2D. That's x and that's y, and there's a z along there. That's a bit dark, so I'll just change the colour. Just move this down. Oh, all this stuff's in the way. How do I do that? Well, I'll do edit draw options instead, and let's make it yellow. So if we now put 3 points on that plane and do a vector from here to here, right click, vector, 2 points, here to here, right click, vector, 2 points. If I now add these two together, that one added to that one, not that one, that one, that's better, that one and that one, and put the answer here. You always have to have a point to put the answer, because obviously these vectors could be anywhere. And right click, vector, add. That's pretty remarkable, isn't it? You get another vector on the same plane, and I think that's very important. Now the Nat 5 syllabus doesn't really go in much further than that, but obviously later on you have a lot of fun with cross products and intersecting planes and lines and all of that. Just a quick reminder that Autograph has all previous pages open, just sitting up here quite happily for you to revise and go back to. And looking at the sort of spectrum of software that's available to you all, Desmos, very, very nice little program and works on anything. It's a fantastic interface. but you can only have one page open at a time, and if you want another page you have to save it and open a new one. And the same with GeoGebra, oddly. I don't know why they've gone for that, but I think it's very, very useful to be able to pop back and to see what you've just been doing. And others trig graphs now, just have a look at those. Let's just see how trig graphs work at all. So if I just do y equals sine x, I should say that we are at the moment, let's just have a look, we're in radians at the moment. The radians degree switch is up here, and if you click OK, you're going to get a graph a bit like that, but it looks pretty horrible without any pi's. So this is where our red tick comes to our rescue again. Ready, steady, boom. There we are. If you don't want those particular scales, you just double click on the axes or axes, edit axes. You can see that it's decided to go in pips of pi by in numbers of pi by 2, but in pips of pi by 4. So there's a pi by 4. There are various other options. Appearance, for example, is quite handy, and you can colour the grid and everything else. You can have subdivisions, say of 4. That makes it look quite graphy. If you like that, you can always delete the graph and just save it as a blank file and then load that up if you're doing some trig work. On the other hand, if we change 2 degrees, what happens? Ooh, it looks very strange, doesn't it? But then if you think about it, 2 pi is about 6, isn't it? So it's hardly got going in degrees. And the red tick comes to our rescue once again. Now if you've got your basic sine wave here, let's see how it can be altered by various transformations. I think it's good to have the host one still there. Let's do y equals a, that'll just be a number, it's 1 to start with, sine, open brackets, b, open brackets, x minus c, close brackets, plus d. Now let's think about that for a minute. A lot of people, including some very reputable books, textbooks that I've seen, put bx plus c here, and that's wrong, because b and c are independent, and b is the frequency and c is the translation to the right, and they are well identified here. But if you put bx plus c, b and c are interdependent, and so it gets a bit messy. Now what do we want for everything? We want, I think A wants to be 1, they're happy with that. B can be 1, but let's make C 0, and let's make D 0. So that should produce a graph pretty much as we've got it at the moment. On top of this one, fantastic. So let's have a look at the constant controller and see what we can do. Can we explore, for example, the amplitude A? As it goes up and down, yes, that's very good. And you've got these invariant points here. Very important for them to realize what they are. Anytime you're doing anything like this, you can have a look at the options. You can do a family plot. That's lots of them. Or you can do an animation up and down. So those are available any old time. So we'll stop it when it's sort of there. That's fine. Let's go back to manual. Okay, that's A. What's B do? B is the frequency. So if you increase B, say to 2, it means you're going to have a complete cycle in just 180 degrees. Let's see if that works. Notice I discussed it and got them to anticipate what's going to happen before. What you mustn't do is just press these buttons and say, oh look. Got to think about it first. Yes, that's fine, that's a complete cycle. What about C? Now because we're in degrees, these numbers here are quite big. We don't want C going up in 0.1s. So let's have C going up in say 15. That should be something quite useful. And you can see that because it's x minus c, it's going to move to the right as we increase c. Yes, there it goes, very happily. And then finally, what's D going to do? It's going to shunt it up and down. So lots to think about there, and understanding how trig functions operate, I think, is very important. So I'll just pause for a second, let you draw breath. I should say that I hope you're not treating this as a workshop. I mean, if you're mighty fast and quick, you can probably follow what I'm doing. But if it's a workshop, we only cover about a third of what we were going to do today. So this is really just to show you the kind of things that AutoGraph's good at. What you will be provided with afterwards is this PowerPoint file linked through the web to all the AutoGraph files. So that will be coming through to you in the next couple of days.
And not forgetting, we've got the 3 training courses already available and free on the Teacher CPD College there, Doug, that people can go and practice and play with AutoGraph. And hopefully Web AutoGraph coming very soon, which would be able to do a lot of these things as well. So.
Yes, I saw the question about iPads. I mean, it'll be wonderful when it's done. It's a major operation to rewrite the whole of this for a different environment, but it's well worth the effort. Okay, shall we move on? That was trig. Now stats. There isn't a lot of stats in your syllabus, but I have discovered that the applications of mathematics has got the rest of the stats in. You've got scatter diagrams, that's about it. Whereas the English equivalent to this has histograms as well. But let's just see what my approach to scatter diagrams is, and we'll start off with a new page. And here we are, new page, and we grab and down to here. Don't want to run this because they're not putting any equations in, so right click, don't show the key. Now here's the point mode, so I'm just going to throw some points on, not too many, and I'm going to select them all, and then going to right click, line, do regression line. Now what does that mean? That means you're taking x as the independent variable and you are trying to anticipate values of y from those values of x. So here are the values of x, and what you're interested in is the difference between that and this. This is the best fit line using a least squares regression, which is a more advanced topic than you're likely to come across at this level. But the proof of it's pretty horrible algebra, but it's lovely to show it dynamically here. This dotted line is very important. You really should not be second guessing what's going to happen to these things outside the range from the data that you've got. So do so with caution. But you can move it around. You see, if we move these points around, the whole thing becomes dynamic. So I'm going to select these points again, and I'm going to group them to a data set. Now what does that mean? It means you can't move them as such, but if you double click, here's the data you've just created. So it is now a data set. This is where you can paste in a data set from a spreadsheet. Okay, so let's have a look at this. You can swap the axes if it turns out to be a useful thing to do. You can scale them by any sort of formula you wish. So lots of possibilities here, but for now we're just going to click OK. We don't want an auto scale, but it's useful to show the stats. So here are the stats. So it gives you the mean, standard deviation. Now in the applications of maths course, I noticed the correlation coefficient is something to be discussed. Click on those and they all wake up, and right click, point, mean. Let's put the mean on. Now there's the mean. Now if you select the mean and the text box is up here. Now it's 3.45, that's it, that's the value, so we'll click that on, and what you get is a nice little box here and a pull out thing, and there's the mean. Now what happens if you move these points? So I'm going to select these points now and right click, line, put that back again. Ooh, it goes through the mean. Does it always go through the mean? Well, in order to move one of these points you have to press the control key. So I'm going to this is the on-screen keyboard, which I haven't mentioned yet. A fantastic little device for putting your mathematical stuff. Lots of mathematical notation here. You can use it outside autograph. You can put it in the middle of an email, whatever. So we want to press Control. Here it is. And then you can move things around. And what you'll notice is that as you do so, the line always includes the mean. And that's very nice to be able to do that. Most applications I've seen of this on the web involve 2 random points, and that's not the right idea at all. So you can show that the mean is always part of the formula. And of course, when you do get the proof of this, it does of course have x minus x bar and y minus y bar as factors. But lots of linear relationships to explore in this environment. And I hope you're putting any questions you may have to Rob in the chat.
Just 1 or 2 coming in the chat, Doug, but we've just been looking at the links to where the beginners, intermediate and advanced course material is. And you're going to share this link at the end, so that'd be great.
Excellent. Is it 4:30 we finish?
It's 20 past 4, Doug, so we've got 15 minutes.
Okay, we've got to get moving then. Right. So we'll move on to the more senior stuff, but we won't have time to show them in the same sort of detail, but I might pick 1 or 2 out from each category. Higher mathematics. I'm sure there are still a number of students staying on to do this course. It's very rewarding and really good to get it done before heading off for university. So let's have a look at the next page. So we've got transformations of graphs, composite and inverse functions, reduction to linear form, trig functions, various calculated skills like area between 2 curves, and a simple introduction to differential equations. Transforming graphs is lovely because in autograph, on a new page, let's get rid of all these, you can see you can enter a function here, and you might want to make your function x minus 3x minus 1, which happens to be my favorite cubic, and you can have a g of x as well and do f of g and all of that. So there's lots to explore there. That's simply defined, so if we now enter the equation y equals f of x, you'll get the equation. There it is. It is my favorite cubic because look at the maximum at -1, the minimum at +1, and the point of inflection at 0. So it's a cracker. But now we can do y equals a f into x minus b. So we can have a look at that, changing a and b. That's going to be a function of x minus b is going to move it to the right of b, and a is going to expand it upwards. But a and b are both 1 to start with. I think I'm going to make b 0. So you don't want to have too much going on to start with, which might cause confusion. So that's just going to, there's a curve right on top of its original one. Constant controller. Now, what's a going to do? A is going to expand it up and down like this, with invariant points here, here, and here. Okay, notice the chat before I pressed any buttons. And what about b? What's that going to do? It's going to shunt the whole thing to the right. Yes. And if you think that's all very well, but what about doing it for something like sin x? Exactly the same. It's the same mathematics. So that's lovely. Obviously, there's more to that, as you can imagine. Inverse functions. Right. This is really, really nice. And it's an interesting topic, this. An inverse function has to work in both directions. So if your parent graph is y equals x squared, you might think that x equals y squared would be the inverse. But it's not, because it hasn't got a one-to-one relationship. If you take a point here and look at its opposite number, there are two possibilities. Let's take a point up here. You've got this one here and this one here, so you don't know which one it is, but obviously this branch and that branch are related. So let's just start this from scratch very quickly. I'm going to put a point on here at -3, 1. Let's have equal aspect. Now I'm going to introduce you, see, in terms of new features, the calculator is fantastic because every object has an attribute and you can use those attributes in any calculation that you wish. And the other one is this XY. You can create a new attribute point based on attributes of what you've got selected. Now I've got this point selected, so its X is -3. But if I want the X of the new point to be the Y of this, and the Y of the new point to be the X of that, that is the seed corn of this topic we're doing. So let's have a look at this. If I click OK, are we going to produce a point that has an X of 1 and a Y of -3? So it's going to be down here. Phew, got it right. Okay, now what happens if I move this one to the right? Where's this one going to go? It's going to go up. And if we do something simple like X, let's do Y equals X -3, just a straight line. And if we attach this point to that line, select that and right click attach to object. This is now going to go up and down, and the inverse is going to be a line that's parallel to it. So obviously there's a lot more you can do with that, but with time constraints we must move on. It's a lovely topic. This is a lovely one as well, but there isn't time to go through this one here, but I just literally put on some points up here with quite a large scale here, and if you enter y equals ab to the power of x plus c, you can ask, it'll draw it, you select it and the data set, and you go best fit to data, and it will find the values of a, b and c, fits it like a glove. Really clever bit of software programming there. And then with this data set, you can, let's just have a look at this. Here's the data set, and if you double click on it, what I'd like to do is to change it to a log scale, so you can reduce this to a linear. Now, x stays where it is, but y, we want to put in log y. Now again, before you press the button to say scale x, what is the log of 1,000? Well, it's 3, isn't it? The log of, these are all 3s, aren't they? Because the next one is going to be 10,000 for 4s. So they're all going to be 3s. Let's just see what that turns out to be like. Yes. So you can see this sort of chat you can have before you press buttons is so important. Okay, I'm going to click OK, but it'll probably look a bit silly because it's still got this graph here. So let's just take this graph off and rescale. And there you have your best fit. You can see that this actually, if we do the line of regression, there's your best fit, straight line reduction of that original data. Lots you can do with trig functions, but I sort of covered this a little bit earlier on, so I think we'll leave that for now. But the way you can link a cos x plus b sin x to this other form, I think, is very powerful and very nice. Calculus skills about areas. Let's have a look at my favorite cubic again. Y equals x minus 3x minus 1, because there's lots you can do to explore the concept of an area under a graph. I'm going to put a couple of points on here, one here. Just wait for the black arrow, and one here. Now if I select this, then this, and right click, create an area. Those who are used to AutoGraph up to this version will probably be wondering where the area has gone, but you can see that you've got these sub-menus which are very important shortcuts to more things. The right-click menu is just getting too long. So anything that isn't a vector, line, circle, or a point goes in the create area. And you have a general area, which is fine. And if you select that, the text box will tell you what the area is. So you can explore things like what happens if you come down here. Oh, well, it's negative, isn't it? Well, of course it is, because all the y values are negative. The x, the delta x's are still positive. So is it possible to have an area that's 0? Well, it certainly is. Around about here somewhere. So, you know, you've got a plus and a minus here, and they can well cancel out. So it's something to bear in mind. The one about the area between two graphs, let's just delete that. Go away. Okay, so I've just got two parabolas here. I've got the intersection here using this tool here and the intersection here. So the logical thing is to select this intersection, then this one, then this graph, then this graph, and right click, create area. Do any of these rules if you wish, but there we are. So it's quite logical and very, very pictorial. Now, I think I said that vectors are my favourite topic, but actually differential equations just about pips it. So let's click OK, and you can see what I've done here. I'll just do it from scratch. Enter equation y prime equals x. Now again, don't press OK yet. Think about it. What does that mean? It means that the gradient, which is y dashed, equals how far you are from the y-axis. So all the way down the y-axis you've got zeros, and over here you've got positives, and over here you've got negatives, which is why it ends up parabolic. Now you can put roots any way you like, but actually there's a much nicer way of doing this. If you double click and look at the startup options, you can use a set of points along the y-axis, and then that tidies that up nicely. If you put a point on here and right click, put a vector of 0, 1, you can see these are all parabolas, and it's a vertical displacement. A lot of people, when you ask them to draw families of parabolas, will draw them with equal normals, but that's it. And what are all these things? Well, if we enter an equation y equals 1/2, there's a half here, x squared plus a constant. C is 1, so that's going to produce a graph there. You can see it is, but I'll just make it a bit thicker. If I select that graph and make it nice and thick, you can see where it is. Okay, so in the last few minutes I'll just take you a quick tour of what else we've got here, because I knew there wouldn't be time to show you them all in detail. But as I say, you will get this file and all the links. Now those of you who are lucky enough to persuade your students to stay on for advanced higher mathematics are in for a treat. There's wonderful topics of calculus, volumes of revolution about either axis, and so on. So let's have a look at some of these pictorially. This good old y equals 2 to the x, and then you change it to a to the x and just fiddle around until these things coincide, but you can zoom in. That's the really powerful thing about that, to produce an introduction to e to the x. Oh, look at that. Isn't that fantastic? Can't resist. Just got time to show you this one. Look, you see, you can go all the way around. Fabulous. Differential equations again, and looking at the discriminant and the damping, it's all there, and x double prime double dot plus 2 lambda x, lambda's the damping, and so on. So a lovely topic, nice and practical. And domain and range is a lovely topic, because here we have I'm just changing the domain here, and it's working out quite cleverly working out the range. Again, it makes a lot more sense if it's done dynamically and things move. Well, there we go. You really should persuade all your students to stay on and do this course. It's just fabulous. There's a nice example of the cross product and two intersecting planes. And complex numbers, wonderful topic. Here, for example, is the cube root of 4, and they all add up to 0, of course. And here's the higher applications of mathematics for those who are not necessarily going into mathematical subjects at university, but a really, really interesting introduction to the, statistics and problem solving. So here's a histogram, and here's the London boroughs of London, multiple box plots. It's a very, really good way of showing lots of data comparatively. And there's a scatter diagram again. Normal distribution, hypothesis tests, and type 1 errors. Beautifully done. There we are in the last minutes. I think that's pretty good going. You can see that it's a very comprehensive program, and it covers a lot of mathematics from a viewpoint of things that move and prove points. There's absolutely no point in doing it if it doesn't do that. So the important thing is to get them curious and then just watch them enjoy it.
Well, hopefully we've made people a little bit more curious about Autograph there, Doug. And remember that it's free to download from the Complete Maths link, completemaths.com/autograph. Obviously, Doug said the autograph files and the PDF for this presentation will be available. And there's also the beginners, intermediate and advanced courses on the Teacher CPD College. So they're well worth having a look at. So thanks, Doug. You've taken us through some fantastic topics there, and I'm definitely going to have to spend a bit more time looking at those when I get a chance. So thanks again, and thanks for coming to the session. So thanks.
Okay. Bye, everybody.
I'd just like to say a quick thanks to Douglas and to Rob. Thanks very much for that session. And I'm just about to put a link into the chat, just as a, well, Yvonne's just beat me to it. She's shared the slide, but I'll put the link into the chat as well in case you don't have a QR reader. Everyone should have also had the link emailed to them, and it would really appreciate if you just take a little bit of time to complete the evaluation. Thank you.